Welcome to the Deep Dive, where we unlock complex topics and equip you with the essential knowledge you need fast. Today we're plunging into the remarkable world of organic synthesis, specifically the art of building complex molecules from simpler ones.
Yeah, it's like molecular Lego, isn't it?
Exactly. But with incredible precision, organic chemistry gives us the exact hooks and tools to connect atoms with, well, surgical accuracy.
Mm.
Our mission today is to demystify two unbelievably powerful reactions that are really at the heart of this molecular construction. The aldol and Clayden condensations.
Absolutely fundamental.
Both are absolutely fundamental for forming new carbon bonds, which, in the world of building molecules, that's basically everything. Our deep dive today is based on the insights from Chapter 26 of Organic Chemistry by Clayden, Greeves, and Warren. Our goal is to really understand the underlying mechanistic logic, trace the pathways these reactions take, and crucially unpack the clever strategies chemists use to control them. So if you're an upper-level undergraduate or just someone fascinated by how chemists can precisely stitch molecules together, you're going to, well, hopefully love exploring these foundational concepts.
And that's exactly it. While both the aldol and Clayden reactions brilliantly form new carbon bonds using enolates, those versatile electron-rich carbons, and carbonyl compounds.
These nucleophilic powerhouses we talked about before.
Precisely. What truly makes them fascinating are the subtle differences in how they work and the ingenious methods chemists have developed to exert absolute control over them.
Okay.
So we'll explore how these reactions transform functional groups, we'll touch on stereochemistry where it's critical, and maybe even see how they fit into retrosynthetic thinking.
Working backwards. Love that.
Yeah, that powerful art of working backward from a desired molecule to its simpler starting materials. It's all about designing with precision.
All right, let's unpack the aldol reaction first. At its core, we're talking about taking remember those electron-rich attacking carbon atoms, basically a negatively charged carbon right next to a carbonyl group,
The nucleophile.
and having it attack the electron-deficient carbonyl group of an aldehyde or ketone.
What's truly elegant here is the inherent simplicity. Imagine you have acetaldehyde. With just a tiny bit of base, like hydroxide, a small amount of its enolate will form.
Just a little bit.
Yeah, just catalytically. This enolate then acts as a nucleophile, seeks out and attacks another acetaldehyde molecule that hasn't formed an enolate yet.
Okay.
It creates a new carbon bond, then a quick proton transfer delivers what's famously called aldol, or 3-hydroxybutanol. That newly formed carbon-carbon bond is the real star.
And the base is catalytic, you said.
Exactly, because it gets regenerated in the final proton transfer step. Very neat.
So if it works with acetaldehyde, can it also work with ketones?
Absolutely. Ketones react beautifully as well. For instance, acetone is a symmetrical ketone, which kind of simplifies things.
Right. No choice of which side to analyze.
Precisely. You don't have to worry about which alpha proton gets pulled off. It behaves in the same fundamental way to give a beta-hydroxyketone. Often, controlling the base concentration is, key to managing this initial step.
Here's where it gets really interesting, though, and where a sort of built-in upgrade often happens. These beta-hydroxycarbonyl products, these aldols, they frequently don't stick around. They dehydrate really easily.
Yeah, that's a crucial point. This raises an important question. Why does this dehydration happen so readily, and what's the synthetic advantage?
Right. Why lose water?
Well, the beauty is that the products formed are highly stable, conjugated systems that we call enols or enols, alpha, beta unsaturated carbonyls.
The double bond next to the carbonyl.
Yep.
That's stable.
Exactly. Think it. You're not just getting an alcohol, you're getting a pre-installed double bond ready for even more complex reactions down the line, like Michael additions or Diels-Alder.
Okay, so how does it happen?
Mechanism-wise. Right. In basic solution, this elimination typically occurs via an E1CB mechanism. The aldol product first enolyzes again.
Pulls off that alpha proton again.
And then that enolate kicks out hydroxide. In acidic solution, it's usually an E1 mechanism. The alcohol gets protonated, water leaves as a good leaving group, and then the molecule forms an enol to stabilize the resulting carbocation and give the conjugated double bond.
So the carbonyl group helps either way.
Definitely. It helps stabilize the intermediate enolate in base, E1CB, or the final conjugated product. And yeah, using stronger bases or higher temperatures really pushes this elimination.
So this ability to form new carbon bonds and then quickly set up a double bond, What does this mean for making new rings, for building cycles?
Oh, it's incredibly powerful for ring formation. Even cyclosystems like cyclopentanone readily undergo the self-condensation and then dehydrate to form conjugated NNO.
Whether you use acid or base.
Whether you use acid or base, yeah. This is a crucial step for constructing more complex fused ring structures. And chemists use clever tricks, too. If a ketone has no alpha protons on one side, like, say, tert-butyl methyl ketone.
The bulky group blocks one side?
Exactly. Or if you're dealing with a cyclic ester, a lactone, it simplifies things dramatically. The analyzation can only happen in one direction, giving you precise control over where that new bond forms.
Okay, now let's pivot to the Clayden condensation. If we start with an ester, like ethyl acetate, and add a base, say ethoxide,
Yeah.
it's pretty similar to the aldol initially, doesn't it?
Indeed, the first steps are quite analogous. You form an analyte from one ester molecule using a suitable base, like the corresponding alkoxide.
So ethoxide for ethyl acetate.
Right, and that analyte then attacks the carbonyl of another unanalyzed ester molecule. But here's the crucial divergence, the clever trick the molecules play.
Okay.
The ester has a leaving group, the alkoxy group, the OR group. So instead of simply picking up a proton like in the aldol reactions intermediate,
Which would just give you a hemiacetal kind of thing.
well, an alkoxide adduct. But here, the tetrahedral intermediate that forms collapses, expelling that alkoxide, in this case, ethoxide.
It kicks it out?
It kicks it out. The result is a beta-keto ester, like ethyl acetoacetate if you started with ethyl acetate.
That's a fascinating twist. So you end up with a ketone and an ester in the same molecule.
Precisely. And here's the real brilliance, the thermodynamic trick. The initial analyte formation and the subsequent attack are actually unfavorable equilibria. They don't really want to go forward much.
Okay, so why does it work so well then?
Because the reaction is driven to completion by the irreversible deprotonation of the beta-keto ester product.
Oh.
This product is significantly more acidic than the starting ester, thanks to having two carbonyl groups flanking those alpha protons. The pKa is much lower.
So the base attacks the product instead.
Yes. The base rapidly and irreversibly pulls off a proton from that beta-keto ester, forming a very stable, delocalized analyte. This step effectively consumes the base and just pulls the entire equilibrium forward, right to the end. It's a masterclass in Le Chatelier's principle.
Wow.
Then you add acid in the workup step to get your neutral beta-keto ester product in high yield.
That's really smart molecular engineering. But I can imagine a potential problem here. If you've got an analyte floating around, why doesn't it just react with the oxygen of the carbonyl instead of the carbon? O attack versus C attack.
That's an excellent question, and it's a general challenge in analyte chemistry. The competition between O-acylation forming things like enol esters versus C-acylation, which is what we want here.
Right.
In the aldol, O attack on an aldehyde or ketone leads to an unstable hemiacetal-like species that usually just reverses.
Right.
But for acylation, especially with highly reactive analytes and highly reactive acylating agents like acid chlorides, it's a real competition.
So how do you control it?
The solution strategy is generally two-pronged. Either you use specific enol equivalents that are maybe less reactive but more selective, like enamines or silane ethers, and you pair them with very reactive acylating agents.
Okay.
Or you use reactive analytes, like lithium analytes, with less reactive acylating agents, like using esters in the Clayden condensation itself. It's about finding that sweet spot, that right balance of reactivity to favor C-acylation.
So self-condensations where one molecule reacts with itself seem pretty straightforward usually. But what if you want to mix and match? Crossed aldol reactions where you combine two different carbonyl compounds. That sounds like it could quickly become a messy soup of side products. How do chemists avoid that?
You've hit on the core challenge of control in basic aldol chemistry. You're absolutely right. Just mixing two different aldehydes or ketones with base often gives you a mess, potentially 4 different products, maybe more if dehydration occurs.
Yeah, a nightmare.
Exactly. So to get a successful crossed aldol, we typically need 2 key conditions to be met. First, only one of your 2 partners should be capable of forming an analyte easily.
Okay, one nucleophile source.
Right. Second, the other partner must be non-analyzable, meaning it has no alpha protons and it needs to be more electrophilic, more reactive towards attack than the analyzable partner.
So it's a good target, but can't attack itself.
Precisely. For example, if you react an analyzable ketone like acetophenone with, say, 4-nitrobenzaldehyde, which has no alpha protons and is super electrophilic because of that electron-withdrawing nitro group, you get a very clean reaction. The aldehyde is the target, the ketone analyte attacks it.
Makes sense.
But if you try to react, say, acetaldehyde with benzophenone, Well, the acetaldehyde will just self-condense much faster because it's both analyzable and a pretty reactive electrophile itself, while benzalphenone is relatively hindered and less reactive.
What about formaldehyde? It seems like the ideal electrophile on paper, no alpha carbons at all, super reactive carbonyls. Surely that's easy to use?
You'd think so. Formaldehyde is incredibly electrophilic, but it's often too reactive for a simple, controlled aldol reaction under basic conditions.
Too reactive. How?
It tends to undergo multiple additions if there are multiple acidic protons, and it's very prone to unwanted side reactions, most famously the Cannizzaro reaction, especially under strong base conditions. In the Cannizzaro, it basically attacks itself, undergoing self-oxidation and reduction. It just leads to complex mixtures. It's just really hard to wrangle effectively in a standard crossed aldol.
So how do we get formaldehyde or something like it to play nice in an aldol-type reaction? Is there a way?
There is a very clever controlled solution called the Mannich reaction. This typically involves an analyzable carbonyl compound, like a ketone, reacting with formaldehyde and a secondary amine, usually in the presence of catalytic acid.
Okay, adding an enamine into the mix.
Yeah, the clever bit is the formation of a highly reactive enamine salt intermediate from the amine in formaldehyde. This aminium ion is a great electrophile.
Ah, so the amine and formaldehyde team up first.
Exactly. This amine salt then acts as the electrophile, reacting cleanly with the enol or enolate form of the carbonyl compound. Mannich products are really valuable intermediates themselves, and they can even be easily converted into reactive enones, alpha, beta unsaturated ketones, which would be very difficult to make directly using formaldehyde in a standard aldol.
Interesting. What about the other way around? Compounds that can form enolates easily but aren't very good electrophiles themselves.
Nitryl alkanes are a perfect example of this. Their alpha protons are surprisingly acidic because the negative charge in the resulting nitronate anion is stabilized by the nitro group.
More acidic than ketones.
Oh yes, much more. pKa values around 10 compared to maybe 20 for typical ketones. This huge pKa difference means even a relatively weak base can selectively deprotonate the nitroalkane in the presence of an aldehyde or ketone.
So you only make the nitrogen anion.
Yeah, exactly. This allows the nitronate to act as a selective nucleophile, attacking the aldehyde or ketone carbonyl in what's sometimes called the Henry reaction or nitro-aldol reaction. It's beautifully selective. In fact, this chemistry is seen in nature.
Really? Where?
Soldier termites actually use it. They synthesize defensive nitroaltenes using this exact type of reaction. Pretty cool.
This brings us nicely to what you call the gold standard for control in these reactions, specific enol equivalents. What exactly are these chemical superheroes and why are they so effective?
Think of them as prepackaged, stable, well-defined nucleophiles. They are stable intermediates that retain the reactivity of an enol or enolate, but crucially, you can prepare them quantitatively, often in isolation, without them self-condensing or doing other unwanted things.
You make the attacker first, then add the target.
Precisely. The beauty is that you first form your controlled nucleophile, get it ready, and then you add the electrophile, the carbonyl compound you want it to react with. This two-step process completely bypasses the messy mixtures you often get in direct crossed condensations.
Okay, what kind of things are we talking about?
We're talking about things like lithium enolates, silly-enol ethers, enamines, alza-enolates, and even the enolates from 1,3,3-dicarbonyl compounds.
Let's start with lithium enolates.
Yeah.
How do we make those precise nucleophiles without them reacting with themselves?
Lithium enolates are typically formed using very strong but also very bulky or hindered bases like lithium disopropylamide, LDA.
LDA, the classic.
The classic, exactly. LDA's bulkiness means it prefers to grab the most accessible proton, which is often from the less sterically hindered side of an unsymmetrical ketone, and it's less likely to act as a nucleophile itself. Crucially, we do this at very low temperatures, like -78 degrees C, which kinetically freezes out unwanted side reactions like self-condensation.
Okay, cold and bulky base.
Right. Once formed, these lithium enolates are incredibly reactive nucleophiles. When you then add your second carbonyl compound, say an aldehyde, the lithium atom often helps organize the transition state. It can coordinate to both carbonyl oxygens in a favored six-membered cyclic transition state.
Ah, chelation control.
Exactly, often leading to very high yields and excellent control, even when reacting with other enolizable aldehydes. This method, pioneered by people like Wittig and Stork, really was a game changer for controlled aldol reactions.
And what about silol ethers? How do those give us control? They sound less aggressive than lithium enolates.
They are generally less reactive, and that's often their advantage. They're usually formed by trapping an enolate, often a lithium enolate or one formed under thermodynamic conditions, with something like trimethylsilly chloride, TMSCl. You replace the proton or the lithium with a bulky silly group.
So they're stable, you can isolate them?
Often, yes. They're much more stable and less basic than metal enolates. Because they're less reactive nucleophiles, they usually need a push to react with an electrophile. This typically involves using a Lewis acid catalyst like titanium tetrachloride,
Like
TPO4.
to activate the other carbonyl?
Precisely. The Lewis acid coordinates to the electrophilic carbonyl, making it much more reactive towards attack by the relatively mild silyl enol ether nucleophile. This controlled reactivity allows for very clean reactions, often avoiding self-condensation issues, like in the synthesis of manicone and ant trail pheromone. There, pentan 3,1 is converted to its silyl enol ether and then cleanly reacts with 2-methylbutanol under Lewis acid catalysis.
You also mentioned conjugated Wittig reagents earlier. Those sound a bit different. How do they fit in as enol equivalents?
Yeah, these are fascinating because they sort of bridge the gap between enolate chemistry and phosphorus chemistry. They're specific enol equivalents derived from alpha-halocarbonyl compounds reacting with triphenylphosphine. They are phosphorus lylids, technically.
Like in the standard Wittig reaction?
Kind of, but they behave like enolates at the alpha carbon. When they react with aldehydes or ketones, they don't stop at the aldol product stage. They bypass it entirely and directly yield conjugated unsaturated carbonyl compounds, the enols or enones.
Straight to the dehydrated product.
Straight to the dehydrated product, often with good control over the double bond geometry, E or Z. They're quite stable, often isolable solids, which adds to their utility as specific, reliable regions.
And what about 1,3 decarbonyl compounds? You said these are maybe the easiest.
They definitely are, in many ways. These are perhaps the oldest and often the easiest specific enol equivalents to use. They frequently don't need special conditions like LDA or extreme low temperatures.
Why is that?
Because the protons between those two carbonyl groups are very acidic, much more acidic than in a simple ketone or ester. Their pKs are often down around 9 to 13.
So easy to remove with mild bases.
Exactly. They're already significantly enolized even under neutral conditions, and their enolates are incredibly stable due to extensive charge delocalization across both carbonyls. A classic example is the Nevinagel reaction.
Nevinagel, right.
That's the condensation of things like diethylmalonate or ethyl acetoacetate with aldehydes or ketones. It's often catalyzed by just a simple mixture of a weak amine base, like piperidine, and a carboxylic acid buffer.
What does the buffer do?
The amine deprotonates the highly acidic 1-baryl-3-dicarbonyl, and the carboxylic acid acts as a buffer, keeping the solution from becoming too basic, which helps prevent the aldehyde or ketone electrophile from enolizing and self-condensing. It's a neat trick.
And you mentioned decarboxylation.
Yeah, a really useful variation is if you use malonic acid itself, or a monoester of malonic acid. After the condensation reaction, the resulting beta-carboxycarbidyl compound readily undergoes decarboxylation upon heating, losing CO2, giving you a straightforward route to alpha-beta unsaturated carboxylic acids or esters. Very handy.
So we've got this amazing array of tools: lithium enolates, silyl ethers, manic, Nevinagel. How do we apply them strategically to different types of carbonyl compounds, especially if we want to be super precise about the outcome?
Precisely, because each functional group presents slightly different challenges and opportunities. Let's take esters, for example. Simple esters, under basic conditions, tend to just undergo Clayden self-condensation, or they might be ignored entirely by more reactive aldehyde or ketone electrophiles in a mixed reaction.
So you can't just mix an ester and an aldehyde with base easily.
Not usually for a clean cross reaction. So for clean reactions using ester enolates as nucleophiles, you really need those specific enolate equivalents we talked about.
Like the lithium enolates.
Exactly. Lithium enolates of esters, which you make carefully with LDA at low temp, or silyl ethers derived from esters, often called silyketene acetyls, or even unique zinc enolates, which are formed in the Reformatsky reaction.
And Formatsky. That's with alpha bromesters.
Right. Alpha bromosters reacting with zinc metal to generate a zinc enolate, which then adds to aldehydes or ketones. We see this need for specific ester enolates in complex synthesis, like the first step in making Himelchain, a natural product, where a lithium enolate of a crowded ester has to react cleanly with an aldehyde.
And aldehydes themselves. You mentioned they're notoriously tricky because they can enolize so easily and act as electrophiles, leading to that messy self-condensation.
They really are the trickiest. Trying to make, say, a lithium enolate of an aldehyde queenly is very difficult because they just react with themselves so darn fast, even at low temperatures.
So LDA isn't the answer for aldehydes.
Not usually for making the enolate itself. Silyanol ethers are a much better approach for aldehydes. You can prepare them using milder conditions, maybe with weak amine bases and TMSCl, which avoids triggering the aldehyde self-condensation. Then you can react that aldehyde-derived silyanol ether with another aldehyde using Lewis acid catalysis.
Okay, silyanol ethers are key.
Or another excellent option, as we touched on, are isoenolates. These are essentially the lithium enolates of enolines, which you form from aldehydes and primary amines first.
Ah, make it an halone first.
Exactly. Deprotonate the enoline with LDA. These enolates are fantastic because they react cleanly and selectively as nucleophiles with other aldehydes or ketones, preventing the messy mixtures you'd otherwise get trying to use the aldehyde directly. For instance, coupling isobutyraldehyde with 3-phenylpropanol works perfectly using the LDA enolate method.
Okay, now ketones, especially unsymmetrical ones, they present their own puzzle. Regioselectivity. If a ketone has two different sides where it can form an enolate, like 2-butanone, how do you control which side gets deprotonated? Which proton gets pulled off?
Ah, yes, the regioselectivity puzzle.
Hmm.
This is where understanding kinetics versus thermodynamics is absolutely crucial. We have two main strategies. The first is to make the kinetic enolate.
Kinetic, the faster one.
The one that forms fastest, exactly.
Yep.
This is usually the enolate formed by removing a proton from the less substituted alpha carbon.
Why is that faster?
Usually for a couple of reasons. Those protons might be slightly more acidic due to statistics, more hydrogens available, like on a methyl group, and importantly, that side is less sterically hindered, so the bulky base can get in there more easily.
Makes sense. How do you make it?
We achieve this using those strong hindered bases like LDA at very low temperatures, typically manically 78 degrees C. The combination of the bulky base and the low temperature locks in the kinetically preferred product. A fantastic example is in the synthesis of gingerol, the pungent compound in ginger.
Oh, yeah.
Yeah, a key step uses a kinetic lithium enolate, made with a base, similar to LDA, LiHMDS, of a protected ketone to selectively react with pentanol, giving an excellent yield of the desired isomer needed for the final structure.
Okay, so that's kinetic, the fast one, less substituted. What's the other option?
The second strategy is to make the thermodynamic enolate. This is the enolate that is more stable, usually the one that's more substituted, leading to a more substituted double bond in the enol or enolate form.
More stable, but forms slower.
Often, yes. You achieve this under conditions where the enolate formation is reversible, under equilibrating conditions. This might involve using a slightly weaker base, maybe a catalytic amount of strong base, or perhaps running the reaction at a higher temperature, or, for a longer time, allowing the system to eventually reach the most stable enolate isomer.
Letting it settle into the most stable form.
Exactly. For instance, if you treat an unsymmetrical ketone with a priotylic base, or even under conditions for making silyanol ethers with trimethylsyl chloride and a base like triethylamine, you often favor the thermodynamic, more substituted silyanol ether. For example, with 1-phenylpropan-2,1, you can selectively form the thermodynamic silyanol ether on the side next to the phenyl group, the conjugated side. These methods give chemists incredible power for precise molecular construction.
Now let's talk about intramolecular reactions. This is where molecules really seem to do some amazing acrobatics. When a reaction like an aldol or Clayden can happen within the same molecule to form a 5- or 6-membered ring, it's often highly favored. Why are these intramolecular versions so easy?
It really comes down to proximity and entropy. Intramolecular reactions are inherently much faster kinetically than the corresponding intermolecular ones when you're forming those favored 5- or 6-membered ring sizes.
Because the reacting ends are already tied together.
Exactly. The reacting groups are already constrained to be relatively close to each other in the same molecule, so the entropic penalty, the cost of bringing two separate molecules together in the right orientation, is largely overcome.
So they find each other much more easily.
Much more easily. Because of this huge inherent advantage, you often don't need the fancy specific enolates or super-controlled conditions you need for intermolecular reactions. Simple equilibrium methods, maybe just a bit of weak acid or weak base, are frequently sufficient to get these cyclizations to go.
Any examples?
Oh yeah. A classic is cyclizing a diketone like cyclodeca 1-phentyl-6-dione. It undergoes an intramolecular aldol condensation to give almost 100% yield of a stable 5-membered ring product. Even with a less symmetrical diketone like nona 2,8-dione, which could potentially form an 8-membered ring or a six-membered ring.
It chooses the 6.
It overwhelmingly chooses to form the less strained six-membered ring via intramolecular aldol, purely because that ring size is so much more favorable than the medium-sized eight-membered ring. Ring strain plays a big role. Even complex unsymmetrical diketones often give a single major product if only one possible cyclization path leads to a stable, conjugated, 5- or 6-membered ring enone.
And then there's the Robinson annulation, which sounds important, a real classic
A truly powerful and famous sequence for building six-membered rings onto existing rings. It's a two-step process that happens in one pot.
2 steps.
Yeah, it starts with a conjugate addition, usually a Michael addition of an enolate, often from a 1,3 diketone or related compound, to an alpha-beta unsaturated ketone, an enone, that forms a new CC bond.
Yeah.
Then the intermediate diketone immediately undergoes an intramolecular aldol condensation.
The aldol closes the ring.
Exactly. The aldol condensation closes the six-membered ring, and it usually dehydrates to give a new fused bicyclic enone system. It was famously used by Sir Robert Robinson and others in early work towards synthesizing the core steroid skeleton structures. It just demonstrates incredible utility in building complex natural products. Definitely a cornerstone of synthetic chemistry.
You also mentioned the Darzens reaction briefly. What does that do as epoxides?
Yes, the Darzens reaction, or Darzens glycidic ester condensation, is another clever tandem sequence. It typically starts with an aldol-like addition of an enolate derived from an alpha-halogenated ester, or ketone, to another aldehyde, or ketone.
Okay, halo ester adds.
Right.
Yeah.
But then instead of just getting protonated like a normal aldol adduct, the resulting alkoxide intermediate immediately turns around and attacks the carbon atom that bears the halogen in an intramolecular SN2 reaction.
The oxygen attacks the carbon with the halogen.
Yes, kicking out the halide ion, like chloride or bromide, and forming an epoxide ring right where the carbonyl group of the electrophile used to be. It's a crucial way to build alpha-beta epoxy esters, or ketones, often called glycidic esters, while simultaneously creating that initial carbon-carbon bond. It complements other methods for making epoxides quite beautifully.
And the Clayden can go intramolecular too, right? The Dykman condensation.
Absolutely. Intramolecular crossed Clayden condensations, generally called Dykman condensations, also strongly favor the formation of those stable 5- or 6-membered rings.
Same reason, proximity.
Same reason, yeah. Proximity makes the reaction much easier. Just like with the intermolecular aldol, even if there are multiple possible enolizable sites on a starting diester, the outcome is often dictated by which cyclization leads to the most stable product specifically. Which beta-keto ester product can form the most stable enolate when the base pulls off that final acidic proton.
So the product stability drives it again.
Product stability is key. You might see examples where a diester could theoretically cyclize to form two different 5-membered rings, but if only one of those resulting beta-keto esters has its acidic proton flanked by both the ketone and the ester carbonyls in the ring, that pathway will dominate because its enolate is so well stabilized.
Clever. Any other tricks with Ekman?
There's a really cunning synthetic strategy sometimes used where two different starting diesters are designed so that their intramolecular Dykman condensation products, after subsequent hydrolysis and decarboxylation steps, actually converge to the same final target molecule, maybe a cyclic aminoketone or something. It simplifies the overall synthesis by allowing for these convergent pathways. Very elegant planning.
Let's circle back quickly to C-acylation, making sure we always attack the carbon, not the oxygen, especially when we're using more reactive acylating agents like acid chlorides, not just esters. How do we ensure that precision? We touched on specific enol equivalents.
Right. We really rely heavily on the principles of those specific enol equivalents again. With very reactive enolates, like maybe a simple ketone lithium enolate, and a very reactive acylating agent like an acid chloride, O-acylation attacking the oxygen to form an enol ester can definitely be a significant side reaction. And sometimes those enol esters aren't even stable to the conditions.
So how do enolamines or isoenolates help?
Well, with specific enol equivalents like enamines from ketones and secondary amines or enolates from enolamanes, any initial acylation that might happen on the nitrogen atom, and acylation is usually reversible. It can easily go back.
Okay.
Crucially, though, the desired C-acylation, the attack on the alpha carbon to form the new CC bond, is generally irreversible. Once that bond forms, it stays formed.
So the irreversible step wins out.
Exactly. This irreversibility effectively drains the system towards the desired C-acylated product, giving you the precision and selectivity you need even with reactive acid chlorides. For instance, in the synthesis of longpheline, a complex natural product, an enamine derived from cyclopentanone reacts cleanly with an acid chloride to give exclusive C-acylation. Aza-enolates, often made from dimethylhydrozones of ketones or aldehydes, are also incredibly useful and regioselective. They often favor acylation at the less substituted alpha carbon, even choosing between a primary and a secondary position, which is a very difficult selectivity to achieve otherwise.
Even with free acids, they have that acidic proton.
Yeah, even acylating things like free carboxylic acids, which obviously have that very acidic OH proton, can be controlled. You typically need to use two equivalents of a strong base, like LDA, to form a dilithio derivative, deprotonating both the OH and the alpha position, or use silynyl ether type chemistry. The key, as always, is to form that stable, well-defined, highly reactive enolate or enol equivalent first, setting up the subsequent attack precisely where you want it to happen.
Wow, okay. We have taken a real deep dive into aldol and Clayden chemistry today. From the basic mechanisms of making those crucial carbon bonds to all these sophisticated strategies for controlling regioselectivity, avoiding side reactions, even touching on stereochemistry. It's clear these reactions were not just fundamental, they are truly indispensable tools in organic synthesis.
Indeed they are. By understanding this subtle interplay of things like PAI values, steric hindrance, reaction kinetics versus thermodynamics, and product stability, chemists really gain the power to precisely build incredibly complex molecules, often with, surprising efficiency and elegance.
Yeah.
These aren't just entries in a textbook chapter. They are the fundamental workhorses that underpin so much of modern chemistry drug discovery, the synthesis of biologically active natural products, the creation of new materials that shape our world. It's hard to overstate their importance.
So thinking about all these powerful tools we've discussed, the enolates, the condensations, the control strategies, what other complex molecular architectures can you, the listener, imagine building now? How might you use an aldol or a Clayden reaction as a key step? Consider the challenges of designing synthetic routes and how knowing these precise reactions gives chemists incredible power to assemble new molecules, literally from the ground up.
And also maybe consider how seemingly small changes, tweaking the structure of your starting materials just slightly, changing the base, adjusting the temperature, choosing kinetic versus thermodynamic conditions can completely alter a reaction's outcome. It really pushes us to try and think like a molecule, doesn't it? And to appreciate the profound elegance and sometimes the frustrating complexity of organic reactivity, the strategic choices of which enolate to form, which electrophile to pair it with, and under what conditions. That's really at the very heart of effective chemical synthesis.
That's all for this deep dive. We hope you've enjoyed gaining these insights and are now, well, even better informed on the fascinating and powerful world of aldol and Clayden reactions. Until next time.